Our next talk is a tale of one software bypass of Windows 8 Secure Boot with Yuriy, Andrew, and Alex. And I want to remind everybody there are survey pods at the back of the room when you leave. If you touch your badge against that will email you a survey that you can fill out and let us know how we're doing, what you think of the speakers and the facilities and all that. We really appreciate everybody doing that. Also, at the end of the talk, if you have questions, there's a microphone over here, just to make sure everybody's able to hear you. Thanks. Yuriy?
Thanks, Nathan. Yeah, thank you everybody for showing up for our presentation. One security guru told me some time ago that if you don't want to sweat presenting to a large audience, you can imagine that the audience is naked. So I'll do that trick. So dudes on the front rows, you're going to be messing with my psychology now. If you could switch with the girls from the audience, that would be great. So anyway, on a serious note, so my name is Yuriy. This is Andrew and Alex. They're my co-workers and co-speakers. They don't really speak English, so I'll do the talking. So whatever questions or concerns you have, please direct them to Alex and Andrew. So anyway, let's get started. So we're here today to talk about the Windows 8 Secure Boot and the problems in implementing Windows 8 Secure Boot on some of the platforms. And this is a rough agenda, really high-level agenda. We'll talk about UEFI, which is the new replacement for legacy BIOSes. We'll talk about the bootkit problem. Then we'll talk about how Windows 8 Secure Boot is solving that problem or intends to solve that problem. Then we'll jump to the security analysis of the implementations of the Secure Boot, and we'll conclude with a set of recommendations. So UEFI and bootkits. This is a rough picture of a firmware software stack on modern PC systems, or not just PC actually. So you have a bottom layer, which is hardware, chipset, CPU, and a bunch of devices, network cards, hard drives, and so on. And you have a system firmware running on top of it, which if it conforms to the UEFI, then standard, then it's a newer software or firmware. In the past, it was a legacy BIOS. Right now, in UEFI terminology, that's the system firmware starts from security phase and then jumps to pre-UEFI initialization phase, where all the bootstrapping of the hardware is happening. And then it loads the so-called driver execution environments, core, dispatcher, so Dixie, which is then responsible for extending the functionality of the UEFI firmware by loading Dixie drivers from, let's say, removable media, hard drive, typically EFI system partition, option ROMs, EFI option ROMs. They're the same Dixie drivers, but they reside on add-on cards like network card or graphics card, or some EFI applications like pre-boot authentication or diagnostic, recovery, update, or like UEFI shell, for example. In order to boot the OS, the UEFI compliant firmware loads bootloaders. It could be, for a Windows case, that could be a boot manager firmware, which is the Windows boot manager, or fallback bootloader, which is boot x64 UEFI, which in their turn load the OS loaders, either WinLoad or WinResume. It's touchscreen, sorry. So depending on whether you're actually booting from cold boot or resuming from S3. So then those loaders are responsible for loading OS kernel, which is in its turn responsible for loading boot time drivers and the rest of the drivers. So where is UEFI in this picture? Reality is UEFI is only the middle of that picture. It's an interface between system firmware, which is platform-specific code. It's not legacy BIOS, but it's still platform-specific. It's a bunch of reference code for bootstrapping chipset, CPU, memory, and so on. And the layer above it and below the OS, that's the UEFI actually. So the benefits of moving to the UEFI from the legacy world is that it's an industry standard interface between the firmware and OS. It's agnostic of the processor or chipset architecture and agnostic, OS agnostic. There is a C development environment, EDK or UDK. It offers a rich GUI-based pre-boot application environment, and it also includes the modular driver model, so you can load drivers to extend your functionality of your UEFI-based BIOSes. UEFI bootkits, when they come to the picture. At the moment, we've now a set of legacy bootkits, which infect NBRs, VBRs, and associated data, but we haven't seen UEFI bootkits. That is mostly because, well, we've seen proof of concepts, but that is probably mostly because the OSs are still booting and using legacy boot through the MBR and so on. So once the OSs move to the UEFI boot, predominantly, then we'll probably see a surge of legacy bootkits moving to the UEFI bootkits. Oh, come on, this is touchscreen. That's interesting. So, yeah. So how UEFI bootkits compromise the system? Assume you've got infected by browser exploit or browser plugin exploit or something. So you have malware on the system, which then can, for example, replace the one of the UEFI bootloaders, fallback bootloader or Windows Boot Manager, and that has been actually demonstrated as a proof of concept in a couple of publications. So, for example, the replacing Windows Manager on the UEFI system partition on the fixed drive, it was demonstrated by in the paper by ITSec. Replacing fallback bootloader, it's what Dreamboot is using in their proof of concept. In addition, the exploit could actually add their own bootloader instead of replacing one of the existing bootloaders. In order to do that, the exploit would need to do some additional actions like modify some of the UEFI system variables, like boot order or boot 1, 2, 3, 4, and so on variables. The other way to install UEFI bootkit would be, instead of replacing bootloader, the exploit could add the Dixit driver, which will get dispatched before the bootloader, and drop that Dixit driver on a UEFI system partition or even removable media. So that, in order to do that, and typically that wouldn't involve patching the BIOS, right? That would be non-embedded Dixit driver, and that would also require changing some variables like driver order, driver 0, 1, 2, 3, and so on. The other option for UEFI bootkits is to replace UEFI-based option ROMs in one of the add-on cards, not embedded. Let's say for a network card, you can see that the network card is in red here, so it kind of shows that the exploit first has to compromise the option ROM on that network card, and this option ROM will get loaded, will get dispatched by Dixit. So that has been demonstrated by Snare last year at Black Hat on MacBooks. So those are, and there are some additional options. For example, the exploit could replace the OS loaders, WinLoad, WinResume. It's a little bit up on the load chain, so that might be not that attractive. But anyway, or the exploit could patch the GUID partition table, GPT, on a hard drive. So there are multiple options for bootkits to get installed. And so once the exploit installed the bootkit, then obviously you cannot guarantee any other boot of the OS. So any further OS component or even firmware component is now compromised and under the control of the bootkit. And more importantly, the bootkit is persistent, so there's no need to run the exploit every time. The bootkit is there forever. You reinstall the OS and the bootkit is still there. And this is an example of our proof of concept bootkit running on the one of the systems that we'll be showing demo on. I'll pause for a couple of seconds. In the recent government leaks, that's an important message, right? So. All right. So like I said, we should expect UEFI bootkits or legacy bootkits move to the UEFI bootkits as soon as the OS has moved their legacy-based, MBR-based boot to the UEFI boot. That's the natural evolution of the bootkits. We'll see them soon. So how that problem generally fixed, or how we want to fix it, right? And the Windows 8 Secure Boot is precisely the architecture that is intended to solve that problem. So let's see how that actually does. Again, the same picture. You have a system firmware, platform specific, running on top of hardware. And this is a root of trust, because this is this system firmware initiates the the secure boot checks, right? So, but the reality is, while this is a root of trust and is supposed to be mutable, the reality is it's just a software on a non-volatile memory, typically a SPI flash, and it has to be updated. It has to be updatable. You have to be able to patch it. So, and that's why, in order for this piece of software to be mutable, it has to rely on that the update mechanism is secure, or let's say signed. So it has to use signed UEFI-based capsule updates, for example. So once this immutable piece of firmware is established and secured through the update mechanism, then it can do the checks on the further component. For example, the option ROMs are all validated, the signatures are validated, or the hashes are validated before dispatching option ROM. The Dixie drivers, which are loaded from non-embedded media like removable or fixed drives, the signatures and hashes are checked. Any application like UEFI shell is checked for signature of it is checked, and more importantly, the OS and bootloaders are also verified before they're loaded and executed. And this is what UEFI Secure Boot is, right? But now we have to continue that chain of verification up until the OS and even further. So the bootloader typically verifies the signature or the hash of the OS loaders, like when load, when resume, which in its turn verifies the kernel, including early launch anti-malware module, which allows antivirus companies to sign their module with Microsoft and load before any boot time driver is loaded, so that they could check those drivers. So. Okay. Yeah, and the OS kernel then is responsible for enforcing signature checks on the OS drivers. Right, so this is Windows 8 Secure Boot, which sits on top of UEFI Secure Boot, and creates the whole picture from the start to the OS. So Secure Boot relies on certain keys to operate correctly and securely. So one of the keys is a platform key. It's a root certificate provided by the platform manufacturer, and it's typically stored in non-volatile memory like in SPI flash. And it is used to verify the update of the key exchange key. And the key exchange key, or a set of keys, it's a set of certificates typically belonging to Microsoft or a platform vendor, or even Linux, or anyone can install actually. So they are used to verify the updates to the next DB and DBX databases. And those databases, DB is a allowed database. It contains X509 certificates, or SHA-1, SHA-256 hashes of the allowed images, of the images that are allowed to boot. In DBX, this is a forbidden database. It contains the same information for the images that are prohibited to boot, that are not allowed to boot. In the earlier versions, DBX contained some other information like directly RSA public keys or the PKCS7 signatures, but not anymore in the newer versions of the UEFI code. So, and there are, in addition to keys, there is some configuration, non-volatile configuration that Secure Boot relies on, and that configuration has certain protections. So let's talk about that. Well, first, the non-volatile UEFI variables. Those are variables that are stored in the NVRAM. They're persistent across all boots. The boot service type of variables. This is the attribute of the variables that says that this variable is accessible at the boot time before the OS runtime, as opposed to runtime attribute, which identifies variables that are writable from the OS runtime. right? So, and typically OS provides an API to the UEFI runtime API to write to those variables. And the protection for secure boot keys is actually coming from the authenticated attribute. That's the attribute for UEFI variables that says that this variable can only be updated if you have a proper private key. So if you can sign the update and this signature can be verified by the certificate in one of the existing variables in NVRAM. So for example, if you update platform key or key exchange key, then you have to sign it with a private key, and the public key it should be in the PK variable already in NVRAM. And so on. So it's not just for a secure boot. Generally, there are other variables that can be authenticated, and you have to have a certificate in a specific CertDB UEFI variable to verify the update. So this is an example of platform key, the master root key for a secure boot on this Asus laptop that we're using for demo. Right. So it's RSA to 2048. Okay, so the other configuration that secure boot relies on is the following on that foil. So there's a master enable disable control which essentially disables or enables secure boot. It's not non-volatile. It's initiated at the boot time. There's a setup mode. Setup mode is a setting for secure boot that says that hey, the platform doesn't have platform key installed. In that case, setup mode is set to setup mode. Otherwise, it's set to user mode. If the UEFI firmware is in setup mode, then the update to key exchange keys or DB, DBX are allowed. So custom mode, that's the mode of secure boot that allows you to update any keys for secure boot, even if platform key is installed, and it's typically should be modifiable only by physically present user. And the last one is secure boot enable. It's the variable. It's a master global enable disable control, similar to the first one, but the non-volatile version of that control. So again, it has to be changed. It has to be modifiable only when the user is physically present, when it approves the change. So there are dependencies on those variables. For example, if platform key doesn't exist, then the setup mode is set to setup mode. Otherwise, it's set to user mode. If secure boot enable variable exists in NVRAM, then and if the value is secure boot enable and the setup mode is in user mode, then the global secure boot is enabled. Otherwise, it's disabled. If secure boot enable variable doesn't exist, then it only depends on setup mode. So if setup mode is in user mode, then we enable secure boot. UEFI firmware. If it's in setup mode, then secure boot is disabled. So it's important to understand those dependencies. There are policies. So for example, when you load you can load images from different places, from embedded firmware volume on the SPI flash, or from removable media, or from fixed media, and the UEFI firmware wants to apply certain policies what to do with those images. So for example, if you load it from embedded firmware volume, then the signatures are never checked. If you're loading from removable media or fixed media, then the corresponding policy is applied. Also, there are policies what to do on signature violation or the security violation. For example, you can ask the user what to do with that image. The signature didn't pass validation or the hash. So, or you can deny execution. So let's have a look at the actual process of validating the images. First, the code, the flow that validates all the loaded images, and this code is registered as a callback. So every time any UEFI-based image is loaded, this code is invoked. Right, so it does those checks. First, it checks policies. Again, if the image is from embedded firmware volume, then it just says, hey, I don't care, load it. I rely on the update, secure update. Or if it's in fixed media, then it takes the policy and applies that policy. If policy says always execute, it just returns without any checks. If policy says deny execute, it returns, it prevents image from loading, again, without any checks. So after checking the policy, it checks configuration. If secure boot is disabled, no need to do any checks. If the file is not in recognized format, then it's not allowed to execute. In earlier versions of the UEFI code, they've been checking some other things, some like secure boot enable directly or setup mode, but now those checks are redundant because they feed into the first check, so it's removed. So, and then once those checks passed, then of course you need to check actual crypto. And essentially hashes or signatures are verified by secure boot. If the image is not signed, then the flow checks for a SHA-256 hash. If it's found in prohibited database, then the image is not allowed to execute. Otherwise, if it's found in the allowed database, then the image is allowed to execute. If the image is signed, then the code goes through all the signatures because PE image can have multiple signatures. And if it finds any signature which is verified by the root or intermediate certificate in the prohibited database, then it blocks the image. Or if it sees that, hey, if the hash isn't DBX, then again it prohibits the image. Then it checks all the signatures. If none of the signatures in the prohibited database, then it checks all the signatures again, and if any signature is verified by the root certificate in the allowed database, then in that case it allows to boot that image, or the hash is in the allowed database. In all other cases, the load is prohibited. This is the latest version, well, at least a couple months old, and the flow is changing over time, so in the past the biases could be built on a slightly different version of the UEFI in reality. So. And this is the secure boot in action on this laptop. So when we try to replace the UEFI, the bootloader, for example, with our bootkit without compromising secure boot first, then we got that screen and we cannot load our bootkit. So as you can see, the Windows 8 secure boot is a pretty important protection against the bootkit problem. So we need to make it, we need to make sure that it's implemented correctly. And with that, we're jumping to attacking Windows 8 Secure Boot. So, as a brief disclosure, the issues are in the implementation of Secure Boot on specific certain platforms, not in the core UEFI or Windows 8 Secure Boot. So, this is the easy and universal exploit against Secure Boot. All you need to do is go reboot your system, enter BIOS setup screen, and there's an option, disable secure boot, so you can click it, disable secure boot, and now you have secure boot disabled. Right? Of course, you need to brute force the key combination to enter a setup screen because all the platforms implement differently, so that's the protection, right? So anyway, I'm messing with you. So this is physical access, right? So secure boot does not prevent physical access attacks. You should be able to go into BIOS setup screen and disable it because you want to run some type of other OS like Linux or whatever. So you need to have a capability to disable it. So it was a joke. So let's get to actual attacks. So attacks are considered in scope are software attacks, basically malware. We think of secure boot as something monolithic, like from Microsoft, developed by Microsoft, and it may have bugs, and bugs will get fixed, and everything will be fine, right? Or at least maybe not that monolithic, but again, monolithic Windows 8 secure boot relying on monolithic UEFI secure boot, but in reality, the picture is different. You have multiple BIOS cores from multiple BIOS vendors, and they implement secure boot differently, slightly differently, maybe not that drastically like I'm showing in the foil, but still differently. And even that net close because we have platform vendors which develop their own BIOSes slightly differently, including secure boot, and configure secure boot slightly differently, and plus they use different BIOS cores. So the picture is much more complex and more interesting than just a monolithic implementation as we may think of it. So based on that picture, you can always conclude that Windows 8 secure boot only secure when all platform vendors and BIOS vendors do a couple of things correctly, and those are a couple of things. They allow signed UEFI firmware updates, only signed updates. They protect the UEFI firmware in SpyFlash from direct modification. They protect the firmware update components because since you sign updates, you have to protect the code that does the update. So if it's either in the SMM or early in the Dixie phase, right? They program spy controller and the flash descriptor correctly. They protect the secure boot enable and all the keys for secure boot in NVRAM. They implement variable authenticated in the SMM and the physical presence checks required to update some of the variables, right? They protect the set variable API. They securely disable compatibility support module, which allows you to boot legacy OS or legacy option ROMs on top of UEFI BIOS. They disable loading legacy option ROMs and the MBR boot. So they configure secure boot secure image verification policies. They build their platform firmware using latest UEFI EDK sources. They correctly implement signature checks and crypto functionality and not introduce a single bug in all of this. So those couple of things that every platform manufacturer has to do in order for a secure boot to be secure. And you know what? Microsoft actually thought about most of them, and they've created a Windows 8 hardware certification requirements, which state most of those requirements. For example, when secure boot is enabled, CSM must not be enabled, right? A secure boot must be rooted in the protected ROM-based platform key. The problem is, well, this is a requirement document. Reality is this is a Microsoft wish list. Right, and the platform vendors do not necessarily adhere to those requirements. So, we're getting to the weak chain, right, of the whole secure boot implementation. So, for example, let's take the first requirement. What if UEFI BIOS updates are not signed? Well, obviously now you're breaking that static core root of trust core root of trust immutability, protection. So you can now update your firmware, including the Dixie image verification lib driver, which is actually responsible for enforcing signature checks just directly in the ROM. So that's a problem. But on this system, we have a implemented UEFI firmware capsule updates using RSA to 2048 and SHA-256. So we are out of luck here. But let's check one little thing. Let's just try to directly write to the firmware code on the SPI flash. And the bottom, the top of that screenshot shows that, hey, we've dumped some of the contents of the BIOS region in SPI flash, and it's all Fs. Then we try to write to it, and you can see that we actually succeeded writing some bogus data, and the data shows that I'm in your BIOS, don't worry, your OS boot has been secured, Black Hat 2013. So we, or the vendor, went to all the pain to implement signed BIOS, UEFI BIOS updates. But the firmware is directly writable. What's the point? Well, there's definitely something can go wrong with that setup, right? So, for example, malware can patch directly the code without going through the update mechanism. So let's see how that exploit works. So you've got an OS exploit, and the firmware is not protected in ROM. So the exploit will go to the directly to the SPI controller, talk to it through configuration registers in MMIO or PCI config space, whatever. We'll program that SPI controller. We'll issue a set of SPI writes and modify directly the firmware on the SPI flash or the NVRAM with all the keys, right? So then after that, the exploit would install the bootkit. And of course, since the firmware, the root of trust is not really, it has been corrupted or modified, then it will not enforce that the bootkit signature checks. So the bootkit will load, and the bootkit, of course, will not enforce any checks on the further components. So now we've got a full boot compromise. So what are the strategies that the Dixie, the exploit could take? First, it could patch directly the code that actually verifies the signatures, but it's platform specific. It's specific on the version of ADK you use to build the firmware. It's specific on the BIOS version or the BIOS core version. So it's doable, but relatively complex. So in addition, instead, the exploit could replace or add the hash of the bootkit or the certificate in the DB allowed database. So now your bootkit is in the allowed database. It is a generic platform independent exploit, but can be easily found by just dumping that DB database and checking for signatures. So anti-malware solutions can easily find that. Similarly, the exploit could add the root certificate into the key exchange key variable, or even the platform key, replace platform key with the bootkit's platform key. And in that case, the signature of the bootkit will be correct. But again, same arguments. It's relatively easy to spot that. So the other strategies that the exploit could take is it can, UEFI defines the global secure boot enable control, and it should be, one bit somewhere, stored somewhere. So it should be easy. Just flip them one bit from 1 to 0 and disable secure boot. But reality is not that simple. So the platform vendors don't really, in most cases, use that variable. They use a very platform and vendor specific places to store that control. And basically, if they're using other EFI variables, then you have to parse the proprietary NVRAM format, and sometimes that's pain in the butt. And even in addition to that, they can actually store multiple copies of that thing in their proprietary NVRAM. So we've implemented that. We've implemented a simple strategy. We just replaced the NVRAM, the whole thing, to the state when secure boot was off. Yeah, it works. But it takes 10 minutes to run the exploit. So it's not that interesting. So and we did parse the proprietary format for most of the BIOSes out there. So this is the proprietary format of the NVRAM on that ASUS system. It's you can see that it actually has linked list of variables. It doesn't store the let's say secure boot enable as 1 or 0. It has a linked list of variables. If secure boot is off, then the pointer to the next variable is all Fs. Or if secure boot is on, then the pointer is actually pointing to some the next variable. So it's a pretty complex thing. So the simple strategy the exploit could take to bypass secure boot is, remember when platform key is not installed, what happens? The system goes into setup mode. Once the system goes into setup mode, secure boot is off. You don't have root key. Well, yeah, you cannot enforce any secure boot. So just make sure that the BIOS will not find platform key. And that could be done by just corrupting the name of the PK variable or the GUID of the PK variable. And in that case, the functionality responsible for signature checks will not find platform key, will enter setup mode, secure boot will be disabled, and it will skip all the checks. And this is a pretty generic exploit. It's independent on the platform or the vendor or anything, and it's 1-bit modification in the flash. So it's pretty simple. And you can see on the left side the platform key for that ASUS system, and on the right side is the same platform key, but we just corrupted the name, just with 1 byte. Oh, sorry, with 1 bit. We flipped, changed PK name to @key. And Windows 8 again, certification requirement states that secure boot must be rooted in a protected ROM or ROM-based platform key. Well, obviously it's not true. So the next spoils will show a couple of screenshots for the exploit. We'll demonstrate live, or we'll try to demonstrate live. So the first screenshot shows that we have fully secure boot enabled. Second screenshot demonstrates the actual exploit. The exploit dumps the NVRAM, searches for a platform key, it finds all the instances of platform key, and flips the bit, basically corrupts the name of each of them in the SPI flash. And it's all installs the bootkit, of course, and it's all done. So upon reboot, if you enter setup screen, then you can see that the BIOS couldn't find platform key. It says it's not installed, although it's there, but it's not installed. It couldn't find it. And of course, since it couldn't find it, then it doesn't enforce secure boot checks on our bootkit. So the bootkit is executing. And when you boot into the OS, you dump the state of the secure boot, and you can see that secure boot is off because setup mode is on, because platform key wasn't found. So that's simple. We'll go to the demo. So Andrew will switch to that laptop, and let's hope that he will not mess with the 2-click sequence of to run the exploit.
Should I show the PowerShell? No. Just exploit?
Just the exploit. So So that's running the exploit, basically the same actions that I've described. It just dumps NVRAM, corrupts the platform keys, disables, of course, write protection for the BIOS, installs the bootkit, and you can now press another button to reboot it. So now after reboot, you can see the bootkit was executed without secure boot checks. And, thanks. And by the way, they did all the work. I do the talking. So, yeah. So while he's booting, he'll show PowerShell. But let me continue for the sake of time. So you can see that if the UEFI firmware is not adequately protected, either in the ROM or during the update process, then subverting UEFI secure boot is possible, but it's not the only thing you should worry about, because the static root of trust for measurement. Oh, okay. I've been actually going through foils, but haven't switched them. All right. So PowerShell. Yeah, so you can see that we've just turned off secure boot from the software. So anyway, sorry, I'm switching. So by passing secure boot when the UEFI firmware is not adequately protected is not the only of your worries. So the static core root of trust used for TCG measured boot and full disk encryption solutions that rely on the TPM, they are also bypassed, right? They are also broken. So here's a couple of papers on that topic that Evil made that compromises full disk encryption solutions with TPM. So the other thing is you can have a malware in your BIOS, even without compromising secure boot or the TPM, right? You can have malware in your BIOS, or as one of the recent government reports told, extremely persistent malware. That's the report where they destroyed a whole bunch of hardware because of the simple malware. So extremely persistent malware. Yeah, I mean, I agree with that. It's if you do whatever you want, you reinstall the OS, the malware is still there. So so that exploit that we showed, it requires kernel mode exploit. Obviously it's important. You get persistence, you get compromised, you compromised everything below the OS, including any security solution below the OS, but still it's a kernel, it's not that interesting. So why not we just go and from user mode modify one of the keys used for secure boot? And if you recall that the keys are protected, they are authenticated variables, so you have to sign them. You cannot just go and directly modify them through the Windows API. The access is denied, right? You have to sign the updates. But we still want user mode exploit. And at the moment we are in the progress of coordinating disclosure with affected BIOS and platform vendors of the multiple findings that we've found during our research. So unfortunately I won't be able to provide the details, but I can offer a demo. And the demo is the same exploit bypassing secure boot, but without any kernel exploit, just a user mode exploit. So I'll do the demo on this laptop as a video. It's the vendor. It's called Censored. Alright, so we're booting Windows 8. Again, just showing that secure boot is actually enabled on this system. So all the signature checks have to be enforced, and you cannot just install bootkit. Okay, so it's enabled. Now launching the exploit, it's a purely user mode exploit. There's even an option no driver. So we loaded the module, installed the compromised secure boot, and installed the bootkit. There are no details in the exploit, but we'll see the result. Again, we've booted bootkit with despite secure boot on this censored vendor. The password is secret. Literally. So now we'll show the state of the secure boot, and there you will see a difference between this exploit and the previous exploit. So you can see that secure boot is now on. It's actually enabled, as opposed to the prior exploit, which showed that it was disabled. So we haven't turned it off. We haven't done anything. We've just compromised it, and the state is showing that it's all on and everything is fine. So none of the antivirus malware would be able to figure this out, I guess. Okay, so now that we've seen that secure boot is possible to compromise, now what? Now, what are the recommendations that we can give to the vendors and to the two mere mortals? Well, first, the recommendations to the platform vendors. It's 2013, so in that year, only signed BIOS updates are allowed and acceptable. And that could be UEFI capsule-based updates or runtime updates from the SMM, either of those methods. The UEFI firmware has to be protected in ROM from direct modification. Using one of the existing hardware mechanisms that the chipsets offer. And that includes not just the firmware, but also the UEFI variable and VRAM store in the ROM. Also, measuring secure boot configuration into PCR7 may prevent or complicate some of the exploit. For example, it can facilitate the detection of the exploit via remote attestation, or the Windows BitLocker can seal the encryption keys to the PCR7. And so if you have an exploit modifying configuration, then the BitLocker wouldn't unseal the encryption key. And that actually is recommended by the Microsoft in their hardware certification requirements. For general end users, make sure that when you buy the system, buy it with the Windows 8 logo, because there is a better chance that the system adheres to the hardware certification requirements, including security requirements for the secure boot. You can check that the update firmware is signed. Disclaimer: you can break their system by bad BIOS update, of course. But basically, just when you get a BIOS update, corrupt it somehow and feed it to the update utility. If it passes the update, you're in trouble. Ask if the platform vendor and how they adhere to the recent NIST BIOS security guidelines, because those guidelines specifically, tell you how to protect the BIOSes. And those are acknowledgements. I'd like to thank you guys for showing up here for our presentation. I'd like to thank Black Hat Committee and Review Board. I'd like to thank certain people, specifically Bruce Monroe for coordinating disclosure and MSRC and Secure Boot team from Microsoft, and certain people who actually helped and supported this work. Don't miss these talks. They're relevant, or they're just cool, or from cool people. Thank you. There's time for questions. There's a mic. If you're, I was joking. You can ask me questions.
Question? Do you see benefit in having a hardware switch to disable UEFI firmware updates so that you flip the switch only when you need to?
Well, you're not protecting UEFI firmware from, reflashing it, connecting the spy programmer to the flash and reflashing the BIOS. So you're not protected from that. So hardware switch would be pretty much equivalent, maybe an easy mechanisms to do that. So I guess, yeah, that's acceptable in my opinion.
Thanks.
Are you by chance going to be sharing these slides?
Sorry, so the question is, will I share the files?
Are you, the slides specifically, will you put them up on a website, or are you going to host them anywhere?
Yeah, Black Hat should be posting them. Let me check with the Black Hat organizers. I think I can send a version.
Thank you.
And yeah, they will be shared definitely.
You mentioned that all vendors should write protect in VRAM so you can't do the kernel mode exploit that you demoed. Do you have any sense of the prevalence of such protection in the current state of platform vendors? Is it just a problem with the particular one that you demoed? Was it the ASUS? How many times are people getting this wrong?
So the question is, what is the prevalence of NVRAM not protected, right? Prevalence of systems, is that correct? Okay. Unfortunately, I probably won't be able to give the number. Well, in reality, I don't know. This is a very specific example of ASUS not doing that. Other vendors may be susceptible to that as well, but I doubt that I can comment.
Did you have to search high and low to find that particular vulnerable platform? Maybe is one way of asking it in a safer way.
Did I search?
Meaning, did you have to buy many different?
I just like ASUS.
Okay.
I use for most of those home systems at home are ASUS, so I just happen to have them.
Thank you.
I haven't worked much in this area, but I've heard about TPM. Using TPM, you can store the keys in the hardware registers itself, and TPM, while booting up, can check up the integrity of UEFI firmware. So is that covered, or?
Can I repeat the question? So basically, your question is whether TPM and the storing of the keys in the TPM would help here.
Yes.
Well, as you can see, that the TPM relies on a certain, it's called static core root of trust for measurements. So a certain immutable piece of firmware that launches first, and it has to be protected, because if it's modified, then you control whatever data is in the TPM. And in that case, if the UEFI firmware is not protected, including that initial piece, it's in UEFI world it's called startup module. In legacy world that was called boot block. If it's not protected, you can modify it. Then using TPM wouldn't help.
Okay, so it's a kind of never-ending process, because gaining the root of trust is really difficult here, right?
I'm really sorry. Could you repeat
So, I mean,
that?
gaining the root of trust is the problem here, because you can never establish that root of trust thing.
Yeah.
Thank you.
Sure. Would you